What is going on, guys? This is Scott with Never Hedge, and today we are going over lesson 3 of the Crypto Zombies Solidity and blockchain development tutorial. This one is going over some advanced Solidity concepts. So buckle up. We're going to stumble our way through it together. All right, lesson 3, advanced Solidity concepts. There we go. Grr, I just can't slow you down, can I? Your Solidity skills are formidable, human. Now that you've got some experience coding Solidity under your belt, we're going to dive into some of the more technical aspects of Ethereum development. This lesson will be a bit less flashy, but you'll learn some really important concepts that will take you closer to building real dApps. Things like contract ownership, gas costs, code optimization, and security. Oh boy. There's a lot of densely packed Solidity knowledge in this lesson, and hopefully you all completed lesson 2 before starting this one. All right. A lot of stuff going on in the first lesson. Luckily, there's only 14 of them. They took pity on us, hopefully. Chapter 1. Immutability of contracts. Up until now, Solidity has looked quite similar to other languages like JavaScript, but there are a number of ways that Ethereum dApps are actually quite different from normal applications. To start with, after you deploy a contract to Ethereum, it's immutable, which means that it can never be modified or updated again. The initial code you deploy to a contract is here to stay permanently on the blockchain. This is one reason why security is such a huge concern in Solidity. If there's a flaw in your contract code, there's no way for you to patch it later. You would have to tell your users to start using a different smart contract address that has the fix. But this is also a feature of smart contracts. The code is law. If you read a code of a smart contract and verify it, you can be sure that every time you call a function, it's going to do exactly what the code says it will do. No one can later change that function and give you an unexpected result. In lesson 2, we hard-coded the CryptoKitties contract address into our dApp, but what would happen if the CryptoKitties contract had a bug and someone destroyed all the kitties? It's unlikely, but if this did happen, it would render our dApp completely useless. Our dApp would point to a hard-coded address that no longer returned any kitties. Our zombies would be unable to feed on the kitties, and we'd be unable to modify our contract to fix this. For this reason, it often makes sense to have the functions that will allow you to update key portions of the dApp. For example, instead of hard-coding the CryptoKitties contract address into our dApp, we should probably have a setKitty contract address function that lets us change the address in the future in case something happens to the CryptoKitties contract. So, what it wants us to do is update the code from lesson 2 to be able to change the CryptoKitties contract address. So we're going to delete the line of code. It says CK address, and change the part that says kitty contract to just declare the variable. And we are going to create a function, where are we, called setKittyContractAddress. It will take one argument address, and it should be an external function. Okay. Inside the function, add one line of code that sets kitty contract equal to kitty interface.address. All right. Remove this. All right. Got step 2 done. And then now we got to set the kitty contract address method here. So we got to make a function. Let me turn off caps lock. That would be helpful. All right, so I don't know if this is correct. Maybe we need a semicolon here. But what I got here, deleted this stuff, created a function set kitty contract address equal to address, and that is external kitty contract equals kitty interface underscore address. Let's see if that is correct. No. All right, so I forgot a couple capital letters. Other than that, pretty much looks okay. And I forgot to, all right, so I'm like 90% of the way there. I forgot to set the address to underscore address. All right, so that wasn't too bad. All right, on to chapter 2, ownable contracts. Now, I did not spot a security hole, but we start out, did you spot the security hole in the previous chapter? The set kitty contract address is external, so anyone can call it. That means anyone who called the function could change the address of the CryptoKitties contract and break our app for all its users. We do want the ability to update this address in our contract, but we don't want everyone to be able to update it. To handle cases like this, one common practice that has emerged is to make contracts ownable, meaning they have an owner, you, who has special privileges. So Open Zeppelin's ownable contract. Below is the ownable contract taken from Open Zeppelin Solidity library. Open Zeppelin is a library of secure and community vetted smart contracts that you can use in your own dApps. After this lesson, we highly recommend you check the site to further your learning. Give the contract below a read through. You're going to see a few things that we haven't learned yet, but we're going to talk about them afterward. And okay, so constructor is a constructor, which is an optional special function that has the same name as the contract. It will get executed only one time when the contract is first created. Function modifiers to only owner. Modifiers are a kind of half functions that are used to modify other functions, usually to check some requirements prior to execution. In this case, only owner can be used to limit access, so only the owner of the contract can run this function. We'll talk more about function modifiers in the next chapter and what that weird underscore semicolon does. Oh boy. Indexed keyword, don't worry about this one, we don't need it yet. So the ownable contract is basically doing the following. When a contract is created, its constructor sets the owner to message.sender, the person who deployed it. It adds an only owner modifier, which can restrict access to certain functions to only the owner. It allows you to transfer the contract to a new owner. Only owner is such a common requirement for contracts that most Solidity dApps start with a copy paste of this ownable contract, and then their first contract inherits from it. Since we want to limit set kitty contract address to only owner, we're going to do the same thing for our contract. So we have a new contract in ownable.sol, and let's go ahead and make the zombie factory inherit from it. Let's modify our code to import the contents of ownable.sol, and we can reference zombie feeding.sol. So pretty simple. Right here, all we got to do is copy that, modify the zombie factory contract to inherit from ownable. Okay, so all we got to do is copy this essentially, and then paste, just set the contract to ownable.sol. Zombie factory dot. Okay. All right, so imported correctly, I think. And then, I think we do this. Luckily, a lot of Solidity seems to be just copy and pasting there. And then I think we got to do is, well, we might not even have to deal with that yet. Let's check this first. Okay, so I did too much here. There we go. Okay, I did too much here. All right, moving on to chapter 3, only owner function modifier. Now that our base contract zombie factory inherits from ownable, we can use the only owner function modifier in zombie feeding as well. This is because of how contract inheritance works. Remember, zombie feeding is zombie factory and zombie factory is ownable. Thus, zombie feeding is also ownable and can access the functions, events, and modifiers from the ownable contract. So this is actually pretty cool. This applies to any contracts that inherit from the zombie feeding in the future as well. And now we're going over function modifiers. A function modifier looks just like a function, but uses the keyword modifier instead of the keyword function. And it can't be called directly like a function. Instead, we can attach the modifier's name at the end of a function definition to change that function's behavior. Let's take a closer look by examining only owner. Okay, interesting. Notice the only owner modifier on the renounce ownership function. When you call renounce ownership, the code inside only owner executes it first. When it hits the underscore semicolon statement in only owner, it goes back and executes the code inside renounce ownership. So while there are other ways you can use modifiers, one of the most common use cases is to add a quick require check before a function executes. In the case of only owner, adding this modifier to a function makes it so only the owner of the contract, i.e. us, me, can call the function. So we are now going to restrict access to the setKitty contract address so that no one but us can modify it in the future. Where is the modifier? All right, so looks like this one is also could be fairly simple. So all we got to do, go here, modify this function to only owner. Maybe. Yep. All right. Chapter 4, going over gas. So now we know how to update key portions of the DApp while preventing other users from messing with our contracts. Now let's look at another way Solidity is quite different from other programming languages, i.e. gas, the fuel Ethereum dApps run on. In Solidity, your users have to pay every time they execute a function on your dApp using a currency called gas. Users buy gas with Ether, so your users have to spend Ether in order to execute functions on your dApp. How much gas is required to execute a function depends on how complex the function's logic is. Each individual operation has a gas cost based on roughly how much computing resources will be required to perform the operation, i.e. writing to storage is much more expensive than adding to integers. That makes sense. So the total gas cost of your function is the sum of the gas costs of all its individual operations. Because running functions costs real money for your users, code optimization is much more important in Ethereum than any other programming language. If your code is sloppy, your users are going to have to pay a premium to execute your functions, and this could add up to millions of dollars in unnecessary fees across thousands of users. So why is gas necessary? Ethereum is a big, slow, but extremely secure computer. When you execute a function, every single node on the network needs to run that same function to verify its output. Thousands of nodes verifying every function execution is what makes Ethereum decentralized and its data immutable and censorship resistant. This is super interesting. The creators of Ethereum wanted to make sure someone couldn't clog up the network with an infinite loop or hog all of the network resources with really intensive computation. So they made it so transactions aren't free and users have to pay for computation time as well as storage. All right. So we're going to go over struct packing to save gas. In lesson 1, we mentioned that there are other types of uints Okay. Normally there's no benefit to using these subtypes because Solidity reserves 256 bits of storage regardless of the unit size. For example, using uint8 instead of uint256 won't save you any gas, but there is an exception to this inside of structs. Oh boy. So if you have multiple uints inside a struct, using a smaller size uint when possible will allow Solidity to pack these variables together to take up less storage. For example, a normal struct here has uint A, B, and C. Struct mini-me saves a bunch of bits by going to uint32 and uint32 for A and B, and then uint is just a normal uint256. For this reason, inside a struct, you want to use the smallest integer subtypes you can get away with. So you'll also want to cluster identical data types together, i.e. put them next to each other in the struct so that Solidity can minimize the required storage space. For example, a struct with fields uint uint32a, and uint32b will cost less gas than a struct with the fields uint32a, uint uint32b because the uint32 fields are clustered together. Good God, this is starting to get a little bit complicated, but not too bad. All right, we are going to put this to the test now. In this lesson, we're going to add 2 new features to the zombies, the level and ready time. The latter will be used to implement a cooldown timer to limit how often a zombie can feed. Okay. Let's jump back into the zombiefactory.sol. So here we are. Add 2 more properties to the zombie struct. Level A uint32 and ready time also uint32. We want to pack these data types together, so let's put them at the end of the struct. Okay. Okay. So I think this is also easy enough. Let's spell uint right, not unit. Uint32 level. Semicolon. Uint32. Where is it? Ready time. And ready and time has a capital T. Also, remember those semicolons. Check the answer. Yes. All right. So now we're going to be adding cooldown time to this using time units. All right, the level property is pretty self-explanatory. Later on, when we create a battle system, zombies who win more battles will level up over time and get access to more abilities. The ready time property requires a bit more explanation. The goal is to add a cooldown period and amount of time a zombie has to wait after feeding or attacking before it's allowed to feed and attack again. Without this, the zombie could attack and multiply 1,000 times per day, which would make the game way too easy. In order to keep track of how much time a zombie has to wait until it can attack again, we can use Solidity's time units. All right. Solidity provides some native units for dealing with time. The variable now will return the current Unix timestamp of the latest block, the number of seconds that have passed since January 1st, 1970. The Unix time, as I write this, is note Unix time is traditionally stored in a 32-bit number. This will lead to the year 2038 problem when 32-bit Unix timestamps will overflow and break a lot of legacy systems. So if we want our DAP to keep running 20 years from now, we could use a 64-bit number instead, but our users would have to spend more gas and to use our DAP in the meantime. Okay, Solidity also contains the time units, seconds, minutes, hours, days, weeks, and years. These will convert to a uint, the number of seconds in that length of time. So 1 minute is 60, 1 hours is 3600, 1 days is 86400. Okay. So we're going to put this to the test. We're going to create a cooldown feature. So we're going to create a uint called cooldown time is equal to 1 days. Okay. Since we added a level and ready time to our zombie struct in the previous chapter, we need to update the create zombie to use the correct number of arguments when we create our new zombie struct. So we got to update the zombies.push line of code to add 2 more arguments, 1 for level and uint 32. And the uint 32 is going to be equal to now plus cooldown time for ready time. Okay. Where is zombies.push? Okay. Here's zombie.push. And we have to... Okay. Not entirely certain how to do the level. Okay, first, let's do this one. Let's define the cooldown time. Uint cool down capital T time equals 1 days. Semicolon. Okay. Easy peasy. Now, can we just do uint 32 level and oh, hang on. I think I know what we need to do. We got to go level equals 1, I believe. And okay. Ready time equals uint 32 now plus cool down time semicolon maybe. Probably not. No. Show me the answer. Show me potato salad. So this one was a little off. Can't win them all. And we have to delete these fuckers. All right, chapter 6. Zombie cooldowns. Now that we have a ready time property on our zombie struct, let's jump to zombie feeding.sol and implement a cooldown timer. We're going to modify our feed and multiply such that feeding triggers a zombie's cooldown and zombies can't feed on kitties until their cooldown period has passed. And this will make it so zombies can't just feed on unlimited kitties and multiply all day. In the future, when we Add battle functionality will make it so attacking other zombies also relies on the cooldown. First, we're going to define some helper functions that let us set and check a zombie's ready time. Okay. So you can pass a storage pointer to a struct as an argument to a private or internal function. This is useful, for example, for passing around our zombie structs between functions. The syntax looks like this. Function, do stuff, zombie storage, underscore zombie, internal, do stuff with zombie, okay? This way we can pass a reference to our zombie into a function instead of passing in a zombie ID and looking it up. So what we're going to do here is we're going to define a trigger cooldown function. It will take one argument, a underscore zombie, a zombie storage pointer. The function should be internal, okay? Next, create a function called isReady. The function will also take zombie storage argument named zombie. It'll be an internal v function and return a bool. Okay. The function body should return zombie.readyTime equals now, which will evaluate to either true or false. This function will tell us if enough time has passed since the last time the zombie fed. Good fucking God. Okay. So, I think this could be... I screwed up a couple times. I think I screwed up this part here. Didn't return the bool with the parentheses. Let's try it again. Got it. Boom. Done. All right. Chapter 7. Public functions and security. Now, let's modify the feed and multiply to take our cooldown timer into account. Looking back at this function, you can see we made it public in the previous lesson. An important security practice is to examine all of your public and external functions and try to think of ways users might abuse them. Remember, unless these functions have a modifier like only owner, any user can call them and pass any data they want to them. Re-examining this particular function, the user could call the function directly and pass any target DNA or underscore species they want to. This doesn't seem very game-like. We want them to follow the rules. On closer inspection, this function only needs to be called feed on kitty, parentheses, empty parentheses, closes parentheses. So the easiest way to prevent these exploits is to make it internal. Currently, the feed and multiply is a public function. Let's make it internal so that the contract is more secure. We don't want users to be able to call this function with any DNA they want. Let's make the feed and multiply take our cooldown time into account. First, after we look up myZombie, let's add a require statement that checks isReady and passes myZombie to it. This way the user can only execute this function if a zombie's cooldown time is over. At the end of the function, let's call trigger cooldown myZombie so that feeding triggers the zombie's cooldown time. So scrolling down, make this function internal. Easy peasy. Add a check for isReady is here. Okay. All right, so don't know if this is right. This is my first attempt. All right, this pretty easy. Just change this from public to internal. Then here I added require underscore isReady myZombie. And out here, probably need an underscore here and here. All I did was add the trigger cooldown myZombie. Okay, missed a couple of parentheses, and I just put this in the wrong spot. Okay, I see what I did there. So I added this at the end of the sequence when I should have just put it right here. But I got it mostly right. Just forgot the parentheses. And then all I did wrong on this one is I did not capitalize the Z. Try again. Okay. We're like 90, 85% of the way there on all of these. So that's good. That means we're learning. All right. So we have a new contract here, zombiehelper.sol. We're on chapter 8. Our zombie now has a functional cooldown timer. Next, we're going to add some additional helper methods. We've created a new file for us, zombiehelper.sol. It imports the zombiefeeding.sol, which will help keep our code organized. Let's make it so zombies can gain special abilities after reaching a certain level. But in order to do this, first we're going to need to learn a little bit more about function modifiers. Okay, previous function modifier was the only owner, but function modifiers can also take arguments. Okay, modifier older than, good, cool. We can see here that the older than modifier takes arguments just like a function does, and that the drive car function passes its argument to the modifier. Let's try making our own modifier that uses zombie level property to restrict access to special abilities. In zombiehelper.sol, create a modifier called above level. Take 2 arguments, a level, a uint, and zombie ID, also a uint. The body should check to make sure the zombie ID level is greater than equal to level. And we have to do the underscore semicolon. So above level. And it's going to take 2 arguments. Uint underscore level. And comma uint underscore zombie ID. Okay. Curly bracket. Not sure if we need require or not, but we'll find out in a minute. All right, this could be completely wrong. Yes. Okay. Now we're on chapter 8 here. More on function modifiers. So great, our zombie now has a functional cooldown timer. Next, we're going to add some additional helper methods. We've created a file that was very nice. The CRYPTOZOMBIES create a file for us called zombiehelper.sol, which imports the zombiefeeding.zol. This helps to keep our code organized. Let's make it so zombies gain special abilities after reaching a certain level. All right, now we are on to zombie modifiers. So let's use our above level modifier to create some functions here. Our game is going to have some incentives for people to level up their zombies. For zombies level 2 and higher, users will be able to change their name. And for zombies level 20 and higher, users will be able to give them custom DNA. And we're going to implement these functions here below. Here's an example code from the previous lesson for reference. So this is what we just did. Now, okay, so we're going to create a function called change name. It's going to take 2 arguments, a zombie ID and a uint, and the new name is going to be a string. All right, you're going to have to reference some old lessons for this one. I forget how to do strings. With the data location set to call data, and let's make it external. It should have the above level modifier and it should pass In 2 for the level parameter, don't forget to also pass the zombie ID. Oh boy. Alright, in this function, first we need to verify that the message to sender is equal to zombie owner and the zombie ID, and we're going to use a require statement. And then the function should be set to zombies, zombie ID name equal to new name. And we're going to create another function called change DNA below change name. And its definition and contents will be almost identical to change name, except its second argument will be new DNA and a uint, and it should pass in 20 for the level parameter on above level, and of course it should set the zombie's DNA to new DNA instead of setting the zombie's DNA. Good fucking God. Alright. Oh, let's piece this apart here. I think we made a string. Oh, okay. Hang on. This might not be quite so hard. I was psyching myself out for no reason. Oh, shit. Have I done this before? Yep. Okay. Okay. We got this. String. Call data. And that data that we're calling is going to be new name. And yep, we do need a capital N for name. Okay. And then this is going to be external. And then we're going to have to make a modifier. Okay. Now we're going to create the second function here. And I'm just going to copy this and then change out new DNA for new name. And that is also going to be external. All right, so we screwed that up a little bit. Had to go back and change a couple things. So let's see if we got it. Got it. Okay. All right. The next one might be, well, might not be that bad. Sounds pretty spooky, but we'll find out soon enough. All right, so chapter 10 is saving gas with the view functions. All right, now that we have special abilities for higher level zombies to give our owners an incentive to level them up, we can add more of these later if we want to. Let's add one more function. Our DAP needs a method to view a user's entire zombie army. Let's call it Get Zombies by Owner. This function will only need to read data from the blockchain, so we can make it a view function, which brings us to an important topic when talking about gas optimization. View functions do not cost gas. That is very good to know when you're evaluating a project and you want to look at a contract, see how much gas their transactions are going to cost. So if they have a lot of view functions on there, it might be a little bit better to invest in because it's not going to cost you any gas. So this is because view functions don't actually change anything on the blockchain. They only read the data. So marking a function with views tells web3.js that it only needs to query your local Ethereum node to run the function, and it doesn't actually have to create a transaction on the blockchain, which would need to be run on every single node and cost gas. We're going to cover setting up web3.js with our own node later, but for now, the big takeaway is that you can optimize your dApp's gas usage for your users by using read-only external view functions wherever possible. All right, so we're going to implement a function that will return a user's entire zombie army. We can later call this function web3.js. If we want to display a user profile page with their entire army, this function's logic is a bit complicated, so it will take a few chapters to implement. So we're going to create a new function named Get Zombies by Owner. It's going to take one argument, an address named owner, and we're going to make it an external view function so we can call it from web3.js without needing any gas. The function should return a uint, an array of uints as memory data location, and we're going to leave the function's body empty now, and we're going to work on that next chapter. Okay, so this one might not be too hard. Function. All right. The function is Get Zombie by Owner. It's gonna return. It's probably wrong, but let's check. Forgot the S. What an idiot. Also forgot returns. And these little bracketies. And the curly brackets. What an idiot. Boom. All right, here, chapter 11. Storage is expensive. One of the more expensive operations in Solidity is using storage, particularly the writes. It's because for every time you write or change a piece of data, it's written permanently to the blockchain forever. Thousands of nodes across the world need to store that data in their hard drives, and this amount of data keeps growing over time as the blockchain grows, so there's a cost of doing that. But in order to keep the cost down, you want to avoid writing data to storage except when absolutely necessary. Sometimes this involves seemingly inefficient programming logic like rebuilding an array in memory every time a function is called because of simply saving that array in a variable for quick lookups. In most programming languages, looping over large data sets is expensive, but in Solidity, this is way cheaper than using storage if it's an external view function, since view functions don't cost your users any gas. Oh, so that's pretty sneaky. We'll go over for loops in the next chapter, but first, let's go over how to declare arrays in memory. Okay. So we can use the memory keyword with arrays to create a new array inside of a function without needing to write anything to storage. The array is only going to exist until the end of the function call, and this is a lot cheaper gas-wise than updating an array in storage. It's free if it's a view function called externally. So this is how we're going to declare an array in memory. So it's going to look like this. And this is a trivial example just to show us how to use the syntax. But the next chapter, we're going to look at combining this with for loops for real use cases. Note, memory arrays must be created with a length argument. In this example, it's going to be 3. So 1, 2, 3, bang, bang, bang. Although this may be changed in a future version of Solidity. Oh, sorry, they can't currently be resized like storage arrays can with array.push, although this may be changed in a future version of Solidity. All right, in our getZombiesByOwner function, we want to return a uint array with all of the zombies a particular user owns. So we are going to declare a uint memory variable called result, and we're going to set it equal to a new uint array. And the length of the array should be however many zombies this owner owns, which we can look up from our mapping with owner zombie count owner. At the end of this function should return a result. It's just an empty array right now, but the next chapter will fill it in. Good God. Okay. Ooh. Okay. Okay, got it. Took a couple tries, but we got there. Not as hard as I thought. Took only a couple tries. All right, this should hopefully be the last hard one. Okay, so for loops. In the previous chapter, we mentioned that sometimes you want to use a for loop to build the contents of an array in a function rather than simply saving that array to storage. Let's look at why. For our getZombiesByOwner function, a naive implementation would be to store a mapping of owners to zombie armies in the zombie factory contract. Mapping address greater than or equal to uint public owners to zombies. Then every time we create a new zombie, we would simply use owner to zombies, owner.push zombie ID to add it to the owners zombies array. And getZombiesByOwner would be a very straightforward function. Would be this. Oh Jesus. The problem with this approach is it's tempting for its simplicity, but let's look at what happens if we later add a function to a transfer for a zombie from one owner to another, which we'll definitely want to add in a later lesson. That transfer function would need to push the zombies to the new owner's owner to zombies array, remove the zombie from the old owner's owner to zombies array, shift every zombie in the older owner's array up one place to fill the hole, and then reduce the array length by 1. Okay. That's a lot of things. Step 3 would be extremely expensive gas-wise, since we'd have to do a write for every zombie whose position we shifted. If an owner has 20 zombies and trades away the first one, we would have to do 19 writes to maintain the order of the array. Since writing to storage is one of the most expensive operations in Solidity, every call to this transfer function would be extremely expensive gas-wise, and worse, it would cost a different amount of gas every time it's called, depending on how many zombies a user has in their army and the index of the zombie being traded, so the user wouldn't know how much gas to send. Since view functions don't call gas when called externally, we can simply use a for loop in get zombies by owner to iterate the entire zombies array and build an array of zombies that belong to this specific owner. Then our transfer function will be much cheaper, since we don't need to reorder any arrays in storage, and somewhat counterintuitively, this approach is cheaper overall. Okay. So this is the syntax for the for loops in Solidity, which is similar to JavaScript. This function will also return an array with the contents 2, 4, 6, 8, 10. Okay. Interesting. So we're going to finish our get zombies by owner function by writing a for loop that iterates through all the zombies in our DAP, compares their owner to see if we have a match, and pushes them to our result array before returning it. Declare a uint called counter and set it equal to 0. We'll use this variable to keep track of the index in our own result array. We're going to declare a for loop that starts from uint I equals 0 and goes up through I greater than zombies.length. This will iterate over every zombie in our array. And inside the for loop, make an if statement that checks if the zombie to owner I is equal to owner. And so we'll compare the two addresses to see if we have a match. Good God. Okay. Inside the if statement, we're going to add the zombie's ID to our result array by setting the result counter equal to I, increment counter by 1. See the for loop example above. Okay. Cool. All right, that one was not as bad as I thought. Still took a couple of minutes to get going, but really it was most of the stuff you were able to figure out by referencing this example. So, all right, enough dilly-dallying. Let's get this thing done. All right, so we're pretty much out of the woods here. Let's wrap this shit up. So, let's go over what we did. We've added a way to update our CryptoKitties contracts. We learned to protect core functions with only owner. We learned about gas and gas optimization. That is huge. We learned about we added levels and cooldowns to our zombies. We now have functions to update a zombie's name and DNA once the zombie gets above a certain level. And finally, we now have a function to return a user's zombie army. So, let's give our zombie an army. All right. We did it. All right, guys. So that is pretty much going to do it for this one. As always, please make sure you are subscribed to the channel for more Solidity tutorials, as well as other NFTs, stocks, and tokens we like. And I thank you guys so much for watching this far, and I will see you in the next video.